Hi, and welcome to Group 20's podcast on symbol tables. A symbol table is a table created by the assembler on its first pass of a DLS source code. On this pass, it records any unique labels such as loop and main, as well as memory addresses such as X and Y. After it stores this label in the table, it records the location counter for that label. That way, when the DLX program is executed and finds a label, it can look on the table and find exactly what it means.
Well, okay, so the purpose of the symbol table is for the program, when assembled, to record the memory location of labels and is effectively the connection between the hard disk memory and the registers. The symbol table is also responsible for the programming convenience, allowing jumps to subroutines to be simple, straightforward to code, and easily adjusted.
Here is our example DLS program, which gives an idea of how a symbol table works in action. This is a simple DLS program that takes a stored memory of X being equal to 5 and it loads it into registry 1. We also initialize R2 to be 0 and we then begin a loop. In this loop, we increase R2 by X, but then we decrement X and we check if X is equal to 0. And then we loop. This loop continues until X is less than or equal to 0, and at which point we finish the program. The result of this is that R2 at the end of the program will be equal to the sum of all the integers between X and 0 inclusive. And now to assemble it. Okay, now we need to assemble this code into DLX. This is done by running through the program and incrementing a location counter at each line. Now the symbol table only cares when we find a label, such as main, loop, done, or X. Whenever we do find these labels, we insert them into the symbol table, where the label is the name of the label, and the address is the location counter at that point. Okay, we're assembling at the first line of the code, which is at location counter 0, and we have found a label called main. Since it's not already in the symbol table, we can insert it into the symbol table with label main and address being the location counter at that point, which is 0. We now have a look at the next line, but since it doesn't have a label, we ignore it for the purpose of the symbol table. We do increment the location counter, and the assembler does use it, but for the purpose of a symbol table, we simply ignore it. The next line, however, which contains a loop, a label, we do look at that quite closely. So, since loop isn't already been inserted into the symbol table, we can add that with label loop and address being the location counter at that point, which is 8. We now continue our way through the code looking for another label, which we find at location counter 1C, which is done. However, there was already a reference to this label earlier in the code, but since it was only a reference and doesn't contain the definition, we ignore it for the purpose of our symbol table. If we didn't contain our definition for done, we would have gotten an error in the assembly. We now know that we have a label at location counter 1C, so we can add it to the symbol table, which is label done at address 1C. We now look at the next line of the code, which is also the last, which has a label called X, containing our variable 5. Now, this isn't a machine instruction, but instead of value, but this is all fair game to the symbol table. And since X hasn't already been inserted in the symbol table, it inserts it in the symbol table, with label X and address being the location counter of 20, which contains number 5, rather than a instruction. And that's how you assemble the symbol table for our basic DLS program. However, there were a few situations that we didn't quite cover in our example program, such as, what if we made an error and we inserted an additional loop label here? The problem would be is that when you assemble it, it would look through, it would insert the first loop just fine, but when it got to the second loop, it would realize, oh no, I've already got one here, which one do I use? And rather than making that tough decision, it instead just crashes, claims there's an error, and doesn't do anything else. But what if this was not an absolute program, but in fact a relocatable?
Well, if it is a relocatable file, then we would have .seg here plus some name. So .seg, some name, code is the politically correct term. And over here, in our memory addresses, we would have plus a $sign representing its relocatable, as well as code. This process will continue throughout the whole symbol table until it reaches the next .seg. Since we don't have one here, it won't. However, this one right here should always be in a .constant segment file.
I'm James Chataway.
And I'm Tony Lloyd.
And you just lost the game! Good night!